All right, guys, let's start talking about chapter 16, which is thermodynamics. So you already touched on thermodynamics in Chem 101, so just some things I want to kind of remind you about that you learned in Chem 101. And the first thing is just like matter can't be destroyed or created, energy can also not be destroyed or created. It can only be transferred. So let's write energy cannot be destroyed / created, only transferred. And so basically what this prevents you from doing is making some kind of perpetual motion machine, right? You can't make that. You can't make more energy than there is, so you can't make some kind of machine that makes more energy than it takes and, solve all the world's problems, that kind of thing. Not going to happen. Right? And so it's the first thing you learn in Chem 101. Another thing you learned about Chem 101 is that energy can be transferred, and it can be transferred so that it can be used. And the main two ways it can be used is to do work, which we generally give the symbol of W, and it can give heat, which we generally give the symbol Q. Right, so that's all I want to remind you from Chem 101. We'll see some little bit stuff later on, right? And Q, you can also think of Q as delta H in terms of us, right? So heat and enthalpy, for the most part, for our class are pretty much the same thing. So another question that thermodynamics really tries to answer is about spontaneity. And basically the question is, will a reaction happen? So our question is, will A turn into B, right? Will A turn into B? Will this reaction happen? And of course, we want to know, how do you know? So let's take a look at it first, an analogy, right? So we can see kind of this is pretty simple in real life scenarios. So we have these hills, right? These guys are hills. There's some kind of valley in between them. And if you go ahead and place a ball here, right, what's going to happen? Well, most of you should be able to predict that this ball is going to roll down this hill. And after some time, right, where it's eventually going to end up is at the bottom of the hill, right? The ball, if you place it up top here, it's going to eventually end up at the bottom of the hill, right? So if we call this state A and this state B, we can say that A will indeed go to B, right? The ball will roll down the hill. So this will happen without outside intervention. Right? If that ball is on top of that hill, it's going to roll down the hill until it gets to the bottom. So this is what's known as a spontaneous process. Right? The ball will spontaneously roll down the hill. But what about B going to A? Right? So up here, will the ball spontaneously by itself roll up the hill? And most of you should be able to answer that question and say no. No, a ball will not roll up a hill by itself, right? So in this type of example, this won't happen without outside intervention. Yes, if you go from the outside and you put the ball up the hill, that can happen, but it won't happen by itself. So this is what's known as a non-spontaneous process. Right, and so for macroscopic examples, it's pretty easy to figure out. Things are generally going to want to go into the lowest potential energy possible, right, to the bottom of the hill. But for chemistry, we want to figure out whether that's going to happen or not. How do we figure that out, right? So spontaneity is relatively easy to predict for the macroscopic world. Right. things will generally fall down, and they'll fall down until they get to some kind of local minimum, some local bottom, right? Let's take a look at some chemical reactions and think about whether they happen spontaneously or non-spontaneously, right? So spontaneous or non-spontaneous. Take a look at iron rusting, water flowing uphill, stuff dissolving, and then a hot pizza cooling to room temperature. So go ahead, pause the video, answer if these processes will be spontaneous or non-spontaneous. All right, so let's take a look at this stuff. Iron rusting, if you just leave some metal out there, it will indeed rust. You don't have to do anything to it. It will indeed rust. So this is indeed a spontaneous process, right? Next example, water flowing uphill. Well, that's not going to happen by itself. Water doesn't flow uphill, same as our ball doesn't climb uphill. Water won't flow uphill. So this is a non-spontaneous process. Next up, we have things dissolving. So if you just toss some sugar in a glass of water without stirring, will it eventually dissolve? And the answer is yes, it will eventually dissolve until the solution becomes saturated. So this is also indeed a spontaneous process. Next up, we've got a hot pizza cooling to room temperature. So, you know, you ordered your hot pizza, you're just letting it sit there on the counter. Maybe you forgot about it. Will it cool to room temperature by itself without you doing anything? And the answer is yes, right? So this is indeed a spontaneous process. So just got a little picture here for you. So on the left here, we have this kind of nice shiny car, and on the right here, it's all rusted, right? So going from left to right, this is indeed a spontaneous process. The car will rust over time by itself. But if you have a rusty car, it'll never unrust by itself, right? Someone's got to actively intervene in there to make it unrust, right? So what we're talking about spontaneity here is, will something happen without outside intervention? If it will, it's spontaneous. If it won't, it's non-spontaneous. And in the macro world, that's pretty easy to predict, but we'll see what happens when we start talking about chemicals instead. So there's an important note here that we have to make, is that spontaneity says nothing about how fast a reaction will occur. So when we're studying thermodynamics and we're studying spontaneity, we're asking, will something happen or will something not happen? We're not asking how quickly it's going to happen. So for example, this rusting, you know, through the use of thermodynamics, we could tell ourselves that this car would rust, but how quickly that's going to take, that's not something we can answer. How fast a reaction occurs, that's the study of kinetics. And so there are two relatively different topics, right? There's not too much interconnection there. So again, thermodynamics, will it or won't it happen? Kinetics, how quickly will it happen? So the example here we can use is a diamond forever, right? This is probably one of the most popular examples out there. So diamond is made only of carbon, but it's sp3 hybridized carbon. So think back to Chem 101 in terms of hybridization. And so coincidentally, so is graphite, which is pencil lead. Graphite is also just made out of carbon. The difference is graphite is made out of sp2 carbon, sp2 carbon. And so if you think about the energetics of the situation, the ball rolling down the hill, graphite is actually lower in energy than diamond, so the ball should roll down the hill. And so diamonds turning into graphite is actually a spontaneous process. It is indeed a spontaneous process. So if you have a diamond ring, it is slowly but surely turning into pencil lead. So that's what thermodynamics tells us. It tells us that it's happening. but it doesn't tell you how fast this is happening. And so if you actually look about the kinetics of this, you'll see that this reaction is super slow. Super slow. And it's so slow that it pretty much doesn't happen. I'll give you an example in a bit. So it's so slow that it pretty much doesn't happen. So when we're thinking about what this is in terms of energy, here we have reaction, here we have diamonds, and here we have graphite. And so graphite is indeed lower in energy, and that's what we're studying when we're talking about thermodynamics. We're talking about these energy levels. Which one is lower in energy levels, right? So this is thermodynamics. And these generally we're talking about state functions. The state functions are things that doesn't matter how you got there, it's just what's the value at the end, right? That's what we're studying. Eventually diamond will turn into graphite because graphite is more energetically stable. And so how it gets there though is a question of kinetics, right? How you got there, that's a question for kinetics. And if you think back to kinetics, this energy hump right here, that's the activation energy. And we said that if you have a large activation energy, your reaction is going to go super slow because you've got to get over this big hump. If you have a small activation energy, you're going to have a fast reaction, right? You're going to get over this hump quite quickly. And so just to give you kind of a numerical value here, at 25 degrees Celsius, 1 cubic centimeter of diamond, in order for it to turn into graphite, so it'll take over 1 billion years. So again, what we're studying in thermodynamics is will a reaction happen or won't it happen? But as we can see here, it says nothing about how fast it happens. So even though diamonds are thermodynamically unstable, they react so slowly that they're known as kinetically stable things. And so again, one of the big goals of thermodynamics is how to predict chemical spontaneity. Wow, all of these beeps on this computer. Whoops, forgot this picture right here. There's a picture of diamond and graphite. So on the left here, you see diamond. These carbons are all these carbons have 4 bonds, so they're sp3 hybridized. And over here you have graphite. These carbons only have 3 bonds each, or are bonded to 3 things, and so they are sp2 hybridized, whereas the diamond bonded to 4 things. Just kind of shove this picture somewhere up here, whatever. Not that important. So if we take a look at this next picture, we can ask ourselves our question, how are we going to determine chemical spontaneity? And it's kind of the same thing that we do in the macro world. So you can see this dude over here is lifting up this weight on this left here, and you can tell that him lifting it up, that's not a spontaneous thing. The weight is not going to go up by itself. The weight will fall down by itself. And so in the macro world, things always want to go to the lowest potential energy in spontaneous reactions. That's the same thing in chemistry. We have a chemical potential, and we always want to get down to the lowest chemical potential. The main question that thermodynamics is asking us right now is, what is this chemical potential? What is this value? What is this property? How can we identify it and then use it to predict whether things are spontaneous or non-spontaneous? The last thing to note here is that spontaneous or non-spontaneous, it just means without outside intervention. So a non-spontaneous action, such as this weight being lifted up, can still happen. It just takes outside intervention. And this outside intervention is actually using spontaneous processes to drive the non-spontaneous process. So that's it for this quick intro onto thermodynamics.